Hello, today I will explain my answer for question 3, rapid deployment with cloud services. In this scenario, university software teams need to build a student project submission platform quickly. The team wants to avoid large upfront server purchases and reduce maintenance work. Because of that, my design uses managed cloud services instead of manually building many servers. The main services are PaaS for the web portal and APN layer, FaaS or serverless fashion for the background jobs, object storage for large project file uploads, SaaS for chat and email notification, and managed AI services for plagiarism detection. At the same time, the platform must follow the basic hybrid network environments. The public web front end can be reached from the internet, but the official student profile and academic record database must remain private in the campus data center. The cloud and campus network are connected through SI2SI and SCC VPN. So, great updates and official student record access happens through a private route, not through the public internet. Now, I will explain the diagram from the left to the right. On the left side, I have the users and public edge session. Students and teacher access the system from a browser or the mobile app using HTTPS, TLS. Their traffic first reaches the CDN and secure DNS. Then passes through WEF and DDoS protection. It means only secure web traffic is allowed to the platform, and common attacks such as malicious web requests or traffic floods can be blocked before reaching to the application. After that, traffic go to the cloud PaaS protocol and unidentified session. The main public application runs a PaaS web portal. This is important for rapid deployment because the software team does not need to buy servers, install operating systems, or manually maintain the web server runtime. The cloud provider manages most of the infrastructure, while the development team focuses on building the submission platform. In the same cloud area, the diagram shows the SaaS cloud identifying provider and OAuth OIDC token and BRAC policy engine. No, my mistake, RBAC policy engine. This part supports test 2, which asks for the student and teacher login and role taking method. User login through the university identity provider using SSO. After login, the system receives OAuth OpenID Connect tokens. These tokens include identity and role information. The RBAC policy engine checks whether the user is a student, teacher, teaching assistant, administrator, or another permitted role. This role check is very important. Students should only access the student dashboard, upload their own submissions, view their own scan result, scan status, and see their own release grades. A teacher should only see submission from courses and sessions assigned to them. The system should not trace only the web front patterns. Every API call must check the token and verify the role on the server side. For teacher and admin accounts, MFA should be required, especially when releasing grades or changing important course settings. In the center of the diagram, I have the student submission dashboard and teacher review and grading dashboard. Student uses the dashboard to upload files and check submission status. Teacher use the grading dashboard to review and clean file. See the plagiarism report, give feedback, and submit grades. This directly supports the required features for the student and teacher dashboard. Below that, the diagram shows the submission processing and SaaS service sessions. This is the one of the most important part of the design. When a student uploads a project file, the file does not go directly to the teacher. It first goes to the temporary object storage for the 1 month. This supports the requirement that late submission is allowed for 1 month. Object storage is better than a traditional file server because it can handle large files, scale automatically, and use lifecycle rules to keep or delete files after the required retention period. After upload, an upload event trigger an FAS virus scan protection. This serverless function starts the anti-malware scanning process. If the file is clean, it moves to the clean submission storage. To this. If malware is found, the file is moved to quarantine storage and an alert is sent to SIEM SOAR. If the virus, go to the alert to this. This ensures that teachers do not open and save file and that the university has evidence for the investigation. The diagram also shows SaaS AI plagiarism detection. After a file passes the virus scan, the platform triggers plagiarism check-in. The similarity report is then connected back to the submission record. So the teacher can review both the file and the plagiarism result. This supports the requirement that an AI tool is used to detect plagiarism in student submission. The same section includes SaaS check service, FAS notification function, SaaS email notification, and SaaS push notification. Instead of building a custom chat server and email server, the team uses many services. When a student submits a project or a teacher releases a grade, the platform publishes an event. A serverless function sends email or push notification. This keeps the main web application first because long-running background tests do not block the user requests. On the right side of the diagram, I have a private campus integration, like this one. The cloud has a cloud VPN gateway, which creates an encrypted site-to-site VPN to the campus firewall. Inside the campus network, the design shows their own PREM student profile API, the PREM student records, and grade systems, and the on PREM student record database private only. This means official student records stay on premises. The cloud application updates grades through a control grade update API. The database is not publicly reachable and only approved private API traffic is allowed. The diagram also includes monitoring and incident response. This one. Logs from WAF API gateway, identity provider, file upload events, virus scanning, plagiarism check-in, VPN, campus firewall, and grade update API are sent to SIEM SOAR monitoring. If malware is detected, SOAR can isolate the upload, disable the user account, block an IP or API key, and create an incident response ticket. This supports the basic security requirements for attack detection, investigation, and automated response. At the bottom, I have the backup and disaster recovery. The design includes cloud backup storage on PREM backup repository, physical secondary site backup, immutable object log backup, and a clean recovery environment. This helps protect upload files, metadata, and official records. If something fails, the system can be restored safely. In conclusion, the design satisfies on both tests. For test 1, it uses PAAS, SaaS, FAAS, serverless storage, managed AI, and hybrid VPN to support all platform requirements with fast deployment and minimal hardware maintenance. For test 2, it uses University SSO, OIDC tokens, MFA, RBAC, and course level authorization, so students and teachers get correct access. Overall, the design supports secure login, file upload, one-man temporary storage, teacher review, grading, chat, email notification, automated virus scan, AI plagiarism detection, private on PIEM student record, and secure grade update through the API. This is all about my explanation for the answer 2 for this question 3. And this is my report for the question 3. Thank you.